All right, so in class you should have started off with the reaction rate activity to see what are the factors that can change a reaction rate. So you should have seen all of them, but now we're going to just go through them so you have notes on it. Right? So what a reaction rate is it's the speed of a reaction. Some reactions happen very quickly and easily, and others are going to take a long time. The exact definition of reaction rate is the rate of decrease of reactants and increase in products. And this definition here is become important when we talk about rate laws, which we'll get to at the end of this. Right? So, what are some factors that affect the reaction rate? The reactants, of course, right? If the reaction rate is what's right when we talked about it of the reaction rate is the decrease in products and the decrease in reactants and the increase in products, the reactants are going to matter. If you're putting in two things that don't react very much, then the rate is going to be slow, versus if you put in something that reacts quickly and is very reactive, then the reaction rate is going to be faster. The temperature also affects it, so affects the reaction rate, right? And typically, a higher temperature, the rate of reaction will occur faster. Of course, there's always a couple of exceptions. Some real-life examples of this, right? Your food doesn't spoil as quickly in the refrigerator because the temperature has decreased, so the reaction is going to slow down. Cold-blooded animals like snakes can't move fast when their bodies are cold. Humans have to maintain a constant body temperature, and the biochemical reactions that keep us alive have to happen at the correct rates. So this is actually why, like, if someone falls into cold water, they won't drown as quickly, and they can recover from it. I think too, like, there's episodes of like Grey's Anatomy or something where they like pack ice on people to slow their body or cool their body temperature to like be able to do work on them more. So that's with the same idea, is if we slow down, if we decrease our body temperatures, the processes slow down and we're able to survive things. As long as it's within a given amount of time, you can't get too cold, of course. Okay. Surface area is also something that will affect it. And the surface area, if you aren't aware, is the amount of, especially on solids, it's the outside area. So if you have something like a box, and this is all that the surface area is this outside of the box, that's not very much surface area. Versus if we have a wire of the same amount, then that's going to increase our surface area. The more places for reactions to take place, the faster the reaction will happen. So powdered substances are going to react faster than a solid substance. This really comes into play with heterogeneous reactions. So this is reactions between different phases. So if we have a liquid and a solid, that's typically what you deal with. And this is because the solid reacting with either the liquid or gas. So if there's more surface, the reactants will react faster. In a biological example, our small intestines have all these microvilli, and so that increases the surface area of our small intestine so that we're able to take in more nutrients. The presence of a catalyst, right? Because these lower activation energy, they will make reactions happen faster by helping get the reactants together. You can think of catalysts like a dating service for chemicals. They bring the chemicals together, and the chemistry happens much more easily than it might happen on its own. And then also, like a dating service, the dating service doesn't go out, right? Just like the catalyst is always there. The dating service is always there. It's just new reactants are coming in, or new people are coming in to date. Then the concentration of reactants matters. If we have a more concentrated solution, then that means that there's more reactants there and they're closer together. So that's going to allow them to react faster because we're going to be able to have more collisions if they're closer together. If you go to this YouTube link, I couldn't figure out how to insert it into this video, sorry. You'll see this reaction take place of hot rust instantly and explosively reacting in, or hot iron rusting instantly and explosively in pure oxygen. This is because normal air is only 20% oxygen. So if we increase the amount of air, then the reaction is going to happen very quickly. So tying into all of these things that we've been learning, right? So we've learned reaction mechanisms, we've learned activation energy and catalyst, and now we've talked about rates of reactions. But we can actually quantify these rates through rate laws. And so these are equations that relate the reaction rate and the concentration of reactants. Because we already know that concentration affects the reaction rate, but with rate laws we can find out by how much it depends on each reaction. So what we have is, if you have a general, we're going to just look at a general reaction here. So little a would be the coefficient, big A is the reactant, little b is the coefficient for big B, the reactant. And because the rate of reaction is the decrease in reactants and the increase in products, rate laws, we only discuss the reactants. So that's why whatever the products are doesn't matter. This is what matters. All right, so how we write this is we have rate, and this is usually written as mole. So big M means molarity, and we'll get into that when we talk about solutions after spring break. But it's basically like concentration per second. Little k here, and when you write little k, I would really want you to write it in the cursive way to show that it's right? Because it's hard, or make it very obvious. Because if you do that, just where it's not super obvious, then that's going to stand for something different in chemistry that we're going to get to. So either exaggerate the top or write it in cursive. Let's see if I can erase those. Okay, cool. Okay, I can't erase them for some reason. Whatever. Okay, so for the rate law, what we have, right, so we've gone to K. Then we have the concentration of our reactants. We put it in these brackets. The brackets are important. They mean something different than parentheses to chemists. And the units for those are those big M's that we'll talk about. And then we have the reaction order, which is little m or little n. But what's important to know is that our little a, so our coefficient of A, is not always the same thing as M. And same thing with the coefficient of B, it's not always the same thing as its reaction order. The reaction order is how important is the concentration to that reaction. Right, so what happens is if we see a 1 here, then that means that concentration only affects it by an order of 1, versus we can have 2 or 3 there. And so that means that the concentration, if we have a with a 2 there, this means that that the concentration of A, this reactant, is going to affect the rate by twice as much, or by another magnitude or another order. And we'll do the same thing depending on what it does. But we need to, this is why we talked about mechanisms, is because the overall reaction is rarely the actual is rarely the actual reaction, right? It's really that small reactions are taking place, and in these steps, right? And typically we're going to have a slow step and a fast step. The slowest step is the rate determining factor, and the rate law is based off of this step. So this is why we learned about mechanisms, and we're coming back to them now that we understand what a reaction rate is. Okay, so let's look at this mechanism here. So this is we have this overall reaction here of NO2 reacting with carbon monoxide to form NO and CO2. And it's broken down into these two steps where one is slow and one is fast. While the rate order, or the rate order wouldn't be affected or isn't necessarily what the coefficients here are, it's always these coefficients though. So for this one, what we get is that we see that it's always based off of the slowest reaction. So for determining the rate law, we don't worry about the fast reaction, we only worry about the slow reaction. And what happens is, if we take, we have our rate, and it's equal to the concentration of the reactants in our slow step, so NO2, and then however many of them we have. So, right, we have 2 NO2s here, so this would be our rate law. And if we look at the answer down here, hopefully I had that blocked out most of the time, we see, and then of course we need our little k in there as well, since that is our rate constant. Right? So how do we find the rate law? If it's so as a scientist, we find it experimentally, and there's some different experiments that you can do to find it, but you don't need to do that for this class. You have to understand what it means and how to get it if I give you a reaction mechanism. I won't ask you to derive it yourself. I will give you the information needed to do it. All right? So hopefully this video helped you with those concepts, and the homework should be applying them.